Hi, welcome to this lesson on National 5 Chemistry for Scotland. This lesson is going to look at the periodic table. We're going to look at the way the elements are arranged in the periodic table. We're going to look at some of the features of the periodic table. And we're going to look at how the periodic table can be useful to us in our chemistry learning. Now, the important thing about chemistry is that it's an experimental science. So a lot of the information that we have in chemistry, or we need for chemistry in order to do experiments and to do research, a lot of that information has been experimentally determined. Okay? It's possible that once quantum mechanics is completely solved, all of these things would be predictable and we'd be able to tell the solubility of something or the density of something just from knowing the rules of quantum mechanics. But unfortunately, quantum mechanics has not been solved completely yet. And as a result, the best information we have is information that has been determined experimentally, which means they put it in tables. Density of something, whether it's a gas or a liquid at room temperature, all of these things have to be looked at in order to find out if they're true. And of course, you're not expected to remember them. You get a whole lot of tables in your exam to look up and use in your chemistry exam. And that's called the data book. The periodic table appears in the data book in various different forms. It spreads the information out through several versions of the table, plus you've got extra information in there to help you. So it's really important to remember that the periodic table is basically a big cheat sheet. You get a data book that's a big cheat sheet. It fills you up. It fills up a whole lot of information, and if you can understand how the periodic table works, then you will be able to use it to your advantage in the chemistry exam. So let's have a look at this version of the periodic table. Now you might say, well, that's not a periodic table. That looks completely different to everything I've seen so far. But one of the things you have to remember is that this is the periodic table that you see is an arrangement of the elements that is useful. But there's lots of different ways to display the periodic table, and this one's quite an interesting one, and it does have a couple of features about it that are really important. So let's look at this. What we have here is we have hydrogen, which is element number 1, stuck up here. You'll notice that it's not the first thing that you see because helium seems to be the first in this list, but let's just look. But here we have our periodic table divide, this blue line. So what we would normally see in the left-hand column of the periodic table, the one over on the left, is these elements here, the ones in red and hydrogen and green at the top. And what we would normally see in the right-hand side of the periodic table are these elements here in blue. They're called the noble gases. Now, if we start here 1, 2, then we go 3, 4, 5, 6, 7, 8, 9, 10. So that's how this table is arranged. But the really important thing about the way this table is arranged is that it shows better the relationship between these three groups, because you can see that they're all next to each other. Normally, when we look at a periodic table, it looks like this group here is stuck way over on one side of the table, and this group here is stuck way over on the other side, and this group here is next to it, but you don't see this one next to it. So these three groups, they're the ones I'm meaning. I might have pointed to these. These three groups are what we're going to talk about in a bit more detail. Now, I say the word groups. A column on the periodic table is a group. Okay, a row on the periodic table is a period. Now, the groups all have chemical properties in common. So all the elements in a group have similar chemical properties. And we're going to talk about these three groups in more detail a little bit later. The rows in the periodic table are called periods. And the periods have one thing in common, essentially. Every element in this period, period 1, has one electron shell. Every element in this period, period 2, has 2 electron shells. Every element in this period, period 3, has 3 electron shells. So the number of the period indicates the number of electron shells in the element. Okay? So get that clear in your head. The number of the period indicates the number of electron shells in the atom of the element, right? Down here, period 4, 4 electron shells. Period 5, we start building up our 5th shell. Okay, now it's all a bit more complicated than that, obviously, but the basic levels, they're called energy levels or orbitals. But just think of them as electron shells for the moment and layers coming out like an onion, right? So What's next? Okay, so the other thing is that the elements in the periodic table are divided into two groups. Generally, we have the metals and the non-metals. Most of the elements in the periodic table are metals, right? That's all these guys down here, and these guys here, and these guys here in gray. Okay? And these guys here in red, and these guys here in, what's that color? Buff. So those are the metals, right? And you'll notice that they make up most of the elements in the periodic table. The non-metals are these guys here in green: hydrogen, carbon, nitrogen, oxygen, phosphorus, sulfur, selenium, and these guys in yellow: fluorine, chlorine, bromine, iodine, whatever those two are called, and then helium, neon, argon, krypton, xenon, radon, and whatever. These haven't been discovered yet. I think that's why they're still unknown, but there's a gap there for them, right? So these are the noble gases, and these are the halogens. That's why they're different colors. And these are the alkali metals. Now we're going to talk about these groups a little bit more later on. Okay, so elements in the same group have the same similar chemical properties, not the same, similar chemical properties, have the same number of electrons in their valence shell. Now we're going to try and understand valency a little bit later. And they make ions with the same charge, right, in general. Because some elements down here, particularly in the transition metals, they can make ions with different charges. So it's not quite as strict as that. But if you stick to these guys up here, these will, except for the noble gases, these guys here will all make ions of the same charge. Okay, let's move on. Right, here's a more conventional view of the periodic table, and this comes from the National 5 data book. And what you see here is that we now can see this staircase. And we also see that these elements here in group 1, this is group 1, and this is group 2, this is group 3, group 4, group 5, group 6, group 7, and group 0 in National 5. We call it group 0. Some people call it group 8. Okay. But we see that this group here has been shoved way over to one side of the periodic table, and this group here has been shoved way over to the other side of the periodic table. But you must remember that they are next to each other, right? It goes 1, 2, and the element next to helium is lithium, right? And the element next to neon, to the right of neon, is sodium. So we've got to remember these guys are next to each other. So or we could put it another way: the noble gas nearest sodium on the periodic table is neon, not argon. And this is an easy mistake to make, because you look at the row and you say, well, it has to be that one because it's on the same row, but it's not. Okay. The other thing you'll notice here, there's a big dark line here, a staircase. It actually extends over here as well. And this staircase represents the division between the metals and the non-metals. Now, there are some elements in here that are not clearly metals or non-metals, and some in chemistry they're known as the metalloids, but we don't have to worry about those in National 5 chemistry. So everything on the left side of the dark line are metals, and everything on the right side of the dark line are non-metals. Okay, it tells you this in the data book. You don't have to remember it. You don't have to remember that for your exam, right? We also see that in each of these boxes we get some information. So we've got a number, then we've got a name, then we've got a symbol, and then we have, in this particular case, we have another series of numbers with commas between them. In this case, it's just the number, the name, and the symbol. Okay, so this is the chemical symbol for this substance, H for hydrogen. That's the name of the element, hydrogen. And number 1 is the atomic number. Now, the atomic number of an element, this is how the elements are arranged in the periodic table. The atomic number represents the number of protons in the nucleus of the atom of that element, right? So hydrogen has 1 proton in its nucleus, helium has 2 protons in its nucleus, lithium has 3 protons in its nucleus, beryllium has 4 protons in its nucleus. Now, they've also got, apart from hydrogen, most hydrogen, they've also got neutrons in their nucleus. But these numbers are important because they tell us how many electrons an atom has of an element. And it's the equivalent, so it equals the protons. So hydrogen has 1 proton and 1 electron. Helium has 2 protons and 2 electrons. Lithium has 3 protons and 3 electrons. Beryllium has 4 protons and 4 electrons, etc., all the way down to the end. Now, the protons don't change in normal chemistry, but the electrons shift around. And so essentially, chemistry is all about the behavior of electrons. And you get that in your head, you're halfway to becoming a chemist. Because what is chemistry? It's the behavior of electrons. Okay? So let's move on. So we're going to talk about the first group, and we'll just go back and have a quick look at that. No. Sorry, we'll just, I was going to go back and have a quick look at this. Remember, we're going to look at this group. This is the alkali metals. We're going to look at this group, which is the noble gases. We're going to look at this group, which is the halogens. So let's get on to the first one. First one is the alkali metals. All of these metals are lithium, sodium, potassium. I've got some videos which I'll probably paste into this video at some point in the future to show some of the reactions of these things. I might cut this video and put it in, but at the moment I'm just trying to get lessons up there, so we'll do the editing later and we'll replace this video. They all have a single electron in their outer shell. So the group 1 represents, the group number represents the number of electrons in the valence shell of an element as well. So if you can remember that, that's handy, in the outer shell. So they easily lose this electron, jump backwards to form an electron configuration similar to the noble gas nearest them in the periodic table, which is what valency is. And they fall back on their lower outer shell. But because they've lost an electron and they have more protons now than electrons, they form 1+ ions. Okay? The reactivity of these things increases as you go down the group. So lithium is the least reactive of these elements, and francium is the most reactive. Obviously, you don't want any of this stuff anywhere near you. Sodium and potassium, I've got some of that in the lab, and we can do experiments with that and show how it reacts, and my students have all seen that. This is the basic general formula when we have M standing for metal in this case, not any particular element. So the metal reacts with water to form hydrogen gas and the metal hydroxide. Okay? Now, hydrogen you'll see is at the top of this group, but it's a bit of an outlier in this group. It's a bit of an exception. Hydrogen is, in effect, an element that's an exception to everything. It's very hard to group because it behaves a little bit like a metal at times, and sometimes it behaves a little bit like a non-metal. And so hydrogen could be placed in this group, or it could be placed in group 7 quite easily. And we'll see why that should be in a future lesson. But the main reason is hydrogen can either gain an electron or lose an electron. It can gain an electron to become like helium, or it can lose an electron completely to become just a proton. Here's our second group that we need to look at. This is the halogens. These are the other reactive elements, the other most reactive elements on the periodic table, and we'll talk about why they're the most reactive, these two groups, in just a second. So, contains the elements fluorine, chlorine, bromine, and iodine that we're going to worry about in National 5. They're all nonmetals. They're all diatomic molecules. They form molecules F2, Cl2, Br2, I2. They have 7 electrons in their outer valence shell, which means that they just need one more electron in order to become like the noble gas nearest them on the periodic table with their electron configuration. So they gain 1 electron. And this is why they're reactive. Getting hold of 1 electron is not energetically difficult, which means that when they get an opportunity to grab an electron, they just grab it. And the same thing applies to those metals that we talked about, the group 1 metals, the alkali metals. They just need to lose 1 electron, and losing 1 electron is much easier than losing 2 electrons. So they're very reactive. So the fewer electrons you need to shift, the more reactive you are as an element in general. Okay? So but in this case, the reactivity decreases down the group. Fluorine is by far the most reactive element, and there's reasons for that, which we're not going to go into in National 5, but you'll learn about them in higher chemistry. Fluorine is the most reactive of this group, and iodine is the least reactive. Also, these elements are quite varied in their physical properties. Fluorine is a gas, chlorine is a gas, bromine is a liquid, and iodine is a solid. So as we go down the group, we move from gas to solid. Okay? This is the general formula for a reaction with what's that? That's hexane, and this This particular reaction is called halogenation. We're going to learn about it in organic chemistry. And bromine can, this is hexene, sorry. Bromine can substitute into, or sorry, add itself into this molecule to form dibromohexane, right? I'm not quite sure why I put that in, but it's something that when we get to that part of the course, you'll be learning about. So this is also known as group 17 and group 7. Okay. So the last group we're going to look at is the noble gases. The noble gases contain elements helium, neon, argon, and krypton. Helium, neon, argon, and krypton, and a few more down here, and a couple of unknowns as we saw in the first table. They cannot form ions because they already have what is a perfect electron configuration. So the electrons do not want to move. I think that down here where the electrons are a bit further away from the nucleus, the electrons can be shifted out, but these first three here that we've got will not form any form of ion, and they'll not form any form of compound. They're all monatomic gases. So helium, in fact, is the smallest normal particle we get in chemistry because hydrogen forms a diatomic gas, helium forms a monatomic gas, so it's actually the smallest particle you can get hold of easily that is still an atom. Electrons can be got hold of, and protons can be got hold of, and proton nuclei can be some nuclei can be got hold of, but this is the smallest atom you can get hold of, normal matter. So helium is used quite a lot to test for leaks in gas systems. They're all very non-reactive, so they're pretty much safe. I mean, you could breathe helium, but it's not much good to you because you need oxygen. But helium will not be toxic. So they cannot form ions. They're all non-metals. And they have the same configuration as the ions formed by elements nearest them on the periodic table. So that's valency in reverse, if you like. Fluorine over here will gain an electron to form the same electron configuration as helium. And sodium here will lose an electron to form the same electron configuration as helium. That's what that means. They're also known as group 8, 18, or 8 in Roman numerals. In our case, in National 5, we call this group 0. Group 0. All right, so let's just summarize that, and then we'll end this video lesson, and you'll be able to do some questions to check your knowledge. So groups 7 to 1 summary. And what I've done here is I've written out a few of them in that order so that it's really easy to see on the table what happens, right? Fluorine can gain 1 electron to become like neon. Sodium can lose 1 electron to become like neon. Chlorine can gain 1 electron to become like argon. Potassium can lose 1 electron to become like argon. So in fact, chlorine gaining an electron and potassium losing an electron, they both end up with the same electron configuration as argon. So they end up with the same electron configuration. One really common substance is a reaction between sodium and chlorine, where sodium loses the electron to chlorine. Chlorine becomes like argon, sodium becomes like neon. All right, so that's basically summarized there in that lesson, in that slide. And if we look at, note that F negative, and sodium positive, which is this is called the fluoride ion. This is the sodium ion, and neon have the same electron configuration. And the chloride ion and the potassium ion and argon all have the same electron configuration. So remember, it's very easy to forget that these guys are next to the noble gas at the end of the previous period. That's what you have to remember, okay? So we will just talk about valency very briefly here at the end of this lesson because I think we've just got a little bit of time. And valency is used to predict the correct formula for chemical compounds. All right, it's the number of electrons an atom needs to lose or gain to have the same electron configuration as the noble gas nearest it on the periodic table. Right? That's chemistry. That one sentence there is pretty much 90% of chemistry. If you get that into your head and figure out how to calculate valency, we'll have a look at that in just a second, you have chemistry pretty much cracked. Okay? Here's the valency. Lithium needs to lose 1 electron in order to be like the noble gas nearest it in the periodic table. Beryllium needs to lose 2. Boron needs to lose 3. Carbon can either lose 4 or gain 4, and it does both. It's a very versatile element. Nitrogen needs to gain 3. Oxygen needs to gain 2. Fluorine needs to gain 1. And for valency, we just remember the numbers. So we go 1, 2, 3, 4, 3, 2, 1, 0. I didn't mean to go back there. 0. And this is why in National 5 we call this group 0. It's to remind us that these elements here have a valency of 0. So there you go. That's a very quick tour through the periodic table. There's some revision in there. There's some new stuff. Quite a lot of revision probably, because you'll have covered quite a lot of this in your BGE learning for science. But get this stuff into your head, particularly this statement about valency, and you'll be doing pretty well there. So on my for my students who are following this course with me, there will be exercises, questions for you to practice your knowledge on this. There are flashcards to practice your knowledge on this in my website. So the website address will be in the links below this video. So if you really, there's 2 things to take away from here, is valency. Figure out valency, and remember that the group 1 metals go backwards. They lose an electron to form the same configuration as the noble gas before them, which are the previous period at the end. They look like they're well separated in the periodic table, but in fact, they're right next to those noble gases. That's the take-home message from this video. Remember that, and valency, and you'll be on the way. I'll see you in the next lesson.